Here we're looking at another example of using both our understanding of how to poke around and analyze functions using pre-calculus and calculus tools, skills, and then also using computer tools in order to get at that. Again, I want to be clear that every technology that you use is going to have different default ways of displaying a graph to you. So you're always going to need to poke around and see if you get another view that gives you all of the features of the function. Okay, and it is interesting, in fact, to ask the question of like what might have been the design decisions made in how a particular digital tool is programmed to show you a graph. And Desmos's decision appears to be that no matter what size your window it is, it gives you an x range from -10 to 10, and then the y range is whatever fits in the screen with a square grid. Okay, so if I change my y range to this, then my or let's do it more. So in this case, my y unit is much shorter than my x unit, and so this gives me a different range. But the default on Desmos is to have a square grid, so that the x and the y have the same unit length. And so if I default to home, it's always going to give me x goes from -10 to 10, and then the y is whatever fits so that it has the same length of unit there. All right, so here is a function that we're going to look at. And I'm not telling you what the function is right now, but we're just going to start by poking around the graph. This is the default view, and it looks like there are some features here. Again, with Desmos, I can click on the graph or click on the equation in the graph. This shows me that it is in this example2 folder, but I'm not going to open that up yet. I get a couple of x-intercepts. It looks like I don't have a y-intercept. This looks like a local, possibly even a global minimum. And but I'm going to poke around. I'm going to zoom out and see if it looks very much like that gives me all of the features of the graph. I can kind of scroll around and see. It looks like 0 might be excluded from the domain. And it really looks like there's nothing interesting happening outside of the things that I see here at the origin. Okay, so I'm going to kind of zoom back in here and then start actually diving in and looking at the function itself. All right, so here's the function. It is a rational function. Right away, thinking about the domain, we can confirm what we saw in the graph, which is that the domain is all real numbers except where x equals 0, which would cause the denominator to be 0. So this would be all real numbers except x equals 0. The range, it looks very much like I get all y values greater than or equal to this lowest y value. This looks like a lowest y value, -3.083. But I'm going to put a question mark, and we're going to come back to this. What is it? 3.083. Okay. Symmetry and periodicity. No periodicity. It looks like none. And I'm going to say none. But I'm going to also do a confirmation that it is not symmetric. this should be pretty easy if I take f2 of -1 versus f2 of +1. So putting in symmetric inputs, -1 and +1, and the outputs are not symmetric and they're not the same. So if the function was even, these numbers would have to be the same. If the function were odd, these numbers would have to be opposites. But they are neither, so that gives me neither symmetry, neither even nor oddness. And we can see that there's no repeats. And I can also confirm the periodicity really only happens if you have trig functions involved. And so rational functions do not have periodicity. Okay. Intercepts. So we saw two that it looks like the function highlighted. So let's put in, let me actually label those. So -6.541. It's supposed to be the point. And something else, (0). What was the other one? -0.459. Negative. Okay. So let's see. Good. So the intercepts come from, like, with a rational function, what makes the numerator equal to 0. This is a second-degree polynomial, so it should have 2 complex roots. We get 2 real roots, so that means that's all of the real roots. Because this is a second-degree polynomial, we actually have a quadratic formula which could give us this. So let's do this. It's -b plus or minus the square root of blah, 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 blah. So a equals 1, b equals 7. I'm just going to copy paste this and bring it down here. So turn that off. So, and I want that. So this is x equals -7 plus or minus square root of b squared is 7 squared minus 4 times 1 times 3 all over 2a. 2 times 1, okay. I don't want this showing. Let's duplicate that, and 7 squared is 49 minus 12. 49 minus 12 is 37. Okay, so there are my 2 roots. These are decimal approximations of them. So I can, if I wanted to duplicate this, I can, so Desmos doesn't really know what to do with this and it's because of that plus or minus. I have a keyboard shortcut that I used for that, but I could look at what is x -7 plus that number and -7 minus that number, and those are the 2 roots that I get. Okay, so there, good. All right, end behavior. So limits at infinity. Oh, end behavior, and also behavior at limits at the edge of the domain. Okay, so the limits at infinity, it looks very much like it is approaching some actual number that looks like not 0. And we can go back here. What is the function again? It is a rational function. And rational functions, you can talk about the end behavior, the limits at infinity, based that they are affected by the relative degrees of the numerator and the denominator. When the numerator and the denominator have the same degree, then the limit is the ratio of the leading coefficients. So this kind of comes from the fact that in this polynomial, for large values of x, the higher power terms dominate that function. So that x squared really dominates that function. And so it behaves a lot like an x squared over x squared, okay, which would be 1. And that's for large values of in the positive direction or in the negative direction. So the limit is 1. So end behavior, limit as x approaches plus or minus infinity is positive 1. Okay, and we can actually put in y equals 1 as a, let me put this in as an asymptote. We can see it looks very much like as I go out very far in either direction, it looks like that it really is approaching that as an asymptote. Okay, fantastic. At the edge of the domain, so that is really x equals 0 is excluded from the domain. So I would want to look at the limit as x approaches 0 from the left and from the right. Looking back at this function, I'm gonna just copy and paste that again. And I'm gonna put something in here to make Desmos not calculate anything with that. So as x gets close to 0, the numerator gets very close to 3 because these terms go to 0. So the numerator gets close to 3. So as x gets very close to 0, the numerator is going to be a positive number eventually, right? When x is close enough to 0, the numerator is going to be a positive number. The denominator is always going to be a positive number because of that square. So for values of x close to 0, this looks like a number that is close to 3 divided by a teensy-weensy number. So if you take 3 divided by a teensy-weensy number and make that teensy-weensy number become teensier and weensier, that quotient is going to explode to positive infinity. So the limit, as x approaches 0, from the left and right, is positive infinity. Okay, great. And I would like to just kind of, let's take this, I'm going to copy and paste this, oops. I'm going to copy and paste this into Wolfram Alpha. Oops. Not sure why that window moved. I'm going to copy and paste this into Wolfram Alpha and look at the limit of that. I'm going to use the natural language input, not the math input. And I'm going to take the limit of that as x approaches infinity. Okay, so this was a copy and paste. Again, this is copying, this has to be typeset in a particular way, and so there is a kind of language for encoding how you typeset it. And this is how you encode that language. Don't worry too much about it. This basically says you have a fraction where this piece is the numerator, and then the second square curly braces is the denominator. Okay, and I can basically, like, I don't have to worry about the lingo. I can just say, I can put in the words that I use to describe this, which is really fantastic about Wolfram Alpha. So this tells me that the limit as x approaches infinity is 1. And then let's look at negative infinity. And the limit as x approaches negative infinity of this function is 1. It does give me a step-by-step solution if you have the Pro account. I am not going to worry about that right now. And I'm going to do also 0. And it looks like it is infinity from both directions. Okay, so I can put, you know, superscript positive, so it looks like the right-hand limit. And it will, if I ask for a one-sided limit, it'll give me both directions. So that's kind of nice. All right, so that's a confirmation for all of those pieces. All right. Intervals of increasing and decreasing. Now, I'm going to go ahead and hide those intercepts now because they're a little distracting. It looks like from Desmos we have, it looks like this is the only key point. This is the only point that where the derivative changes from, or that we have a local maximum or minimum. It's also true that the derivative changes from being positive to negative at x equals 0, but x equals 0 isn't part of the domain. All right, so it looks like this is the only key value, but let's confirm that. Now, in the last example, I took the derivative basically because it was pretty easy. It was a polynomial, and I am going to utilize tools on this. So I am going to copy this, and I'm going to go to Wolfram Alpha. And before I do that, I am going to calculate. I'm going to just ask Desmos for what is my f2 prime of x look like. So this gives me the graph of the derivative. And Desmos is really great for just like no muss, no fuss. It just gives me the graph of the derivative. And so this does show me that the derivative looks like it's negative, and then it crosses from being negative to positive at x equals negative 0.857, and which is the same as the x coordinate of that local minimum. And so this is a really nice thing to see, but again, I want to make sure, I want to use some tools to make sure that I'm not missing any other hidden features that might be out there that are too far or too subtle for me to see. Okay, so it looks like this is my only minimum at x equals negative 0.857. I am going to confirm this by taking this second derivative, taking this function, and I can definitely calculate the derivative by hand. And because I have a tool in front of me, I'm going to use that tool. So I can say derivative of that I copied and pasted. There we go. And it gives me the derivative is negative 7x plus 6 over x cubed. Interesting. So let me double check this. Is y equals negative 7x plus 6 over x cubed. And that looks very much like the same graph of the second derivative. So I feel like I have not accidentally calculated the wrong thing in Wolfram alpha. Okay. And I'm going to turn that off now. I'm going to make this orange. I don't know why I always have to have it orange, but I do. And so now I can actually see from this there's only one place where the derivative is 0 because that is a linear function. So the derivative at x equals, setting this equal to 0 gives me negative 6/7. Okay, so let me label this. This is first derivative. All right, great. So that tells us that, you know, the derivative can't actually cross the x-axis over here, because the only way that it can switch from being positive to negative is either if it goes across the x-axis that way, or if I have a break in the graph, right? Which happens here at x equals 0. So that tells us this is our only key value at negative 6/7, and that gives me a nice number that I don't have to you know, use the decimal approximation. It's here. That negative 0.857 is actually negative 6/7. Okay, and so I can calculate what is f2 of negative 6/7. And I know that this is going to give me an actual rational number, since it's a rational function. So I can ask Desmos to give me the fraction version. So that tells us, what does it tell us? The derivative is negative for all x values to the left of negative 6/7. The derivative is positive for x between negative 6/7 and 0. And then the derivative is negative for all values of x greater than 0. That tells us that the function itself is decreasing for x less than negative 6/7. The function itself is increasing for x between negative 6/7 and 0, and the function is decreasing for all x greater than 0. All right. Okay. Decreasing for x less than negative 6/7 and x greater than 0, and increasing for x between negative 6/7 and 0. Okay. And then this tells us we only have one local maximum or minimum. So we have a local minimum because the derivative switches from being negative to positive. That means the function switches from decreasing to increasing. The output of that minimum output value is negative 37/12 at x equals negative 6/7. Okay. And we can also see that because we have some of the x values are positive to the right of 0, and we confirmed that there are no other roots of the function, that the function never gets below x equals 0, and so it definitely never gets below that negative 37/12 for x to the right of 37/12. And then since f is a strictly decreasing function for x to the left of negative 6/7, that means that as I go backwards on the graph, the the function would be increasing. So this actually tells us that this is the global minimum. So I can actually now confirm our range and say my range is y is greater than or equal to negative 37/12. Okay, or I can say that the range is negative 37/12 to infinity. As an interval. Okay, so now I have settled my range. Like I said before, a lot of times the range gets settled like after you do some other analysis, and that's where that got settled this time. Okay, and I can say this is a global minimum. Okay, intervals of concave up and down. We're going to get, this is going to be second derivative. So I'm just going to take, I could take the first derivative and take the derivative of that. I could also go back to here and say just the derivative of that. And so that gives me the second derivative here. So second derivative, 2 times 7x plus 9 all over x to the 4th. Let's double check that this makes sense, that this is the derivative of the derivative. So the second derivative should be negative where the first derivative is decreasing. The second derivative is positive where the first derivative is increasing. The second derivative is positive where the first derivative is increasing. That looks right. And let's just double check that if I put in f2 double prime of x, that looks like the same function. Looks good. Okay. So again, the second derivative, we only have one root, so we can see there's only one place where it changes, the derivative changes sign by crossing the x-axis, and then there's the x equals 0 where it's excluded from the domain is the only opportunity for the derivative to change sign otherwise. So we only have one place where the second derivative is 0. So at x equals, setting 7x plus 9 equal to 0, that would be negative 9/7. So that would tell us that that would be our only point of inflection. This is where the second derivative, let me get rid of that first derivative, it's confusing things. Okay, so where the second derivative switches, if the second derivative is negative, that tells us that the function itself is concave down. If the second derivative is positive, that tells us the function itself is concave up. So it looks like I have a point of inflection right around here, which feels about right in terms of looking at the shape of the graph. So let's take a look at what is f2 of negative 9/7. And I'm going to go ahead and allow Desmos to give me a fraction for that. And it looks like negative 9/7 and negative 71/27 is the point of inflection. And I'm going to put that under here. And I'm going to say, so the second derivative is negative for x to the left of negative 9/7. So f2 is concave down for x less than negative 9/7. And then here it's concave up for x to the right. Oops. For -9/7 less than x less than 0. And then for x to the right of 0, that means the second derivative is positive, so the original function is concave up, which is what we see. So we put and x greater than 0. Super. I think we have completed all of the things. So this, all of the information that we've been given does actually tell me that I have like all of the key information for this graph can be found here. Okay, so I can, maybe I want to, like if I was to plot some of this, I might want to plot the absolute minimum, so -6/7 and -37/12. Oops. We might label those if we wish. Unfortunately, Desmos doesn't label it with fractions. If I wanted to, I could actually put in, I could copy this and that would copy the math formatting. And if I put that between two of the back quotes, those back quotes are usually up into the, like above your left tab. So there it is. And I will put a, oops, how about if I just copy this whole thing and paste it here. There we go. Then that gives me the formatting for the math there. Super. Okay, and I can actually do that the same for the point of inflection. Copy this, and give me a back quote, and put that in there. There we go. So this tells me all of that information that I need to know for that function.